So today's lecture is going to be focusing on chemistry, specifically reactions and kinetics. We're going to talk a little bit about balancing equations, but then we'll spend most of the day on equilibrium and kinetics, so rates of reaction. Okay. Again, if you weren't here last week, personal introduction. My name is Mark Abdurrahmanov. I'm an undergraduate senior at Stony University. I'll be finishing up my Bachelor of Science in Biochemistry in about 1 month. My MCAT date was January 16, 2021, so only about 2-3 months ago. I scored a 520, and here's my score breakdown. My contact information, here's my email. Feel free to email me anytime if you have any questions or concerns, or if you want any help or anything like that. Okay. So I'm going to describe this course a little bit. So right now we're doing the 8-week program, which has lectures every Sunday at 12 p.m. And we also have office hours every Saturday from 12 p.m. to 2 p.m. Where you can just come in and ask me questions, kind of more like a one-on-one type thing. Every week we'll cover a different topic, alternating between the 4 MCAT sections. Last week we did biochemistry. This week we're doing chemistry. Next week we're doing cars. After that, we'll move on back to bio and then psych and so on. Once this ends on June 6th, we're planning to launch a 15-week full course. So during this, we'll do 3 lectures a week, 1 to 2 office hours a week, and we'll cover most of the highest yield MCAT content. So this 8-week program, only 8 lectures. We're not going to be able to cover nearly as much as we want for the MCAT. During the full 15-week, we will be able to cover much more. And the planned start is the week of June 14th. Okay. All right. So we can start moving on to the content. So learning objectives for today, we just want to review stoichiometric balancing of equations and determining oxidation number. Oh, if the email here, 1 second, I can go back to the email. Here you go. If everybody wants, can you take a picture or just write it down or something? And then the email will come up again at the end if you want to wait for that. Okay. All right. So we want to review stoichiometric balancing equations determining oxidation number. I expect most of you will kind of remember this from general chemistry, so I won't spend too much time on it. Most of the time will be spent on understanding what equilibrium means and how it is maintained. We also want to understand chemical kinetics and rate laws, especially the equations. And we want to know the equations for the equilibrium constant, the rate determination, and the difference between the equilibrium constant and the rate constant. Okay. So first, we have to balance equations. This is very important, but very basic. I'm sure most of you already know this. The general rule is anything that appears on the left also has to appear on the right. So you see on the left, there's this glucose and oxygen. There's 6 carbons in this glucose. So that means there must be 6 carbons on this right side of the reaction, right? Since there's only CO2 is the only carbon containing molecule, there must be 6 CO2s in order to make 6 carbons, okay? Same thing with hydrogen. You have 12 hydrogens here. So that means you must have 12 hydrogens on this side. H2O is the only hydrogen containing compound. So it must equal 12 total hydrogens. So you would also have a 6 here, 6 H2Os to make 12 hydrogens because there's 2 hydrogens per water. And oxygen, there's 6 here. And if we have a 6 here and a 6 here, that means there's 6 plus 12, 18 oxygens on the right side. That must mean there's 18 on the left side. There's 6 here, so it leaves 12. That means there must be 6 O2 as well on the left side. And I will show you that right here. So this is what it looks like when it's fully balanced. As I mentioned, 6 CO2 for the carbons, 6 H2O for the hydrogens, 6 O2 to make sure there's 18 oxygens on both sides. And ATP is just, it's a form of energy. It's a cofactor. We'll talk about that more when we do Krebs cycle. All right. The general rule, the number of each atom on the left must be equal to each element on the right. Oxidation number, also pretty simple. You can kind of think of it as the charge on each molecule in a compound. So for example, in this Fe2O3, you know that the overall charge of the compound is neutral, it's 0, but that doesn't mean everything here is neutral. Each of these irons and oxygens is actually charged. So how do you determine the charge? Well, there's some common oxidation numbers that you should know. So for example, all of the column 1 elements like sodium, potassium, all have a charge of +1, pretty much always. All of the column 2 elements like magnesium, calcium, they almost always have a charge of +2. Oxygen pretty much always has a charge of -2, except when it's bound to fluorine, in which case it's positive, but that's a very, very rare situation. Pretty much always oxygen is -2. Halogens like chlorine, fluorine, they're pretty much always -1. Okay. Whereas something like iron, like Fe, or any of the transition metals, which I will show right here. So you can see group 1, lithium, sodium, potassium, always +1. Magnesium, calcium, these guys are always +2. Column 2, this last column, fluorine, chlorine, bromine, they're almost always -1. Oxygen is -2. That rule doesn't always apply to all of the other elements here. Like all these column 16 ones aren't always -2, so be careful with that. Only oxygen. Okay. And from there you can figure out anything else that they give you. So for example, these transition metals in the middle, these purple guys, the Fe, manganese, cobalt, nickel, copper, they usually have different oxidation states depending on what they're bound to. They could be +2, +3, +4 sometimes. It depends what they're bound to. And that's what the questions will usually ask you to find out. So in this case, you know that oxygen is -2 always. So there's 3 oxygens. That means a total of -6. You know the compound in general is neutral, 0. So that means the 2 irons together must equal +6 to balance out. That means each iron is +3. And it's, so iron has, in this case, has an oxidation number of +3. Right? So these you should kind of like have memorized. It's pretty simple if you just look at the columns. And then from there, you can figure most out. This is an example, like I mentioned, you can see sulfur in the middle. It's in the same column as oxygen, so you would expect it to be -2, but that's not always the case. So like I mentioned, sodium is always +1, so that's +2. Oxygen is always -2, so that's -8. That actually gives you a grand total of -6. You know it's neutral, so it means sulfur in this case is actually +6 rather than -2. Okay. Any questions on that so far? Yes, you do get a periodic table on the MCAT, yes.
You said, sorry, you said the sulfur is ±6 instead of what now?
So in this case, if you count everything up, so the 2 sodiums are each +1, that gives you a total of +2. Then the 4 oxygens are each -2, that gives you a total of -8. You combine -8 with +2, you get a total of -6. In order to balance out the -6, that means sulfur, which is the only remaining molecule left in this compound, must be +6 in order to make the whole compound neutral.
Okay, that's what I.
So yeah, so in this case, sulfur is +6. Yeah. All right. Now here we get to the real lecture. So starting with equilibrium and kinetics. So we know that reactions occur, but we want to also find out how quickly they occur. Determining the rate of a reaction is a very important process for just chemistry, for biology, biochemistry, all of that. So how do we do that? Well, there's this handy equation. Rate equals rate constant times the concentration of the reactants to the power of the order of the reaction with respect to the reactant. I know that's a little bit confusing, so we can take it one step at a time. So rate is kind of what you're trying to find, and it's measured mostly in the change in concentration over time. That's the most like simple way to put it. And you can see here, I don't really like the way they wrote it here because they did moles per meter squared per second. So if you remember what concentration is moles per liter. and liter is about the same as meter cubed. It's a volume. So that's how they wrote it. But mostly you can think of it as just change in concentration over time. Okay. All right. So it's raised mostly change in concentration over time. Rate constant, it's, as you may guess from the name, it's a constant, but it's a constant only for the specific reaction we're looking at. So each reaction has its own rate constant, okay? And I don't want to get into the units of rate constant because they're a little bit confusing and I don't believe you really need to know them. So we want to move on to these A and B in hard brackets. These are the concentrations. These will almost always be concentrations of the reactants, okay? So you don't want to put concentrations of the products or any intermediates in these, only the reactants. And then you see these exponents. So these exponents are what's called orders. So each reactant contributes to the rate of the reaction in different ways. So some reactants contribute more to the rate of the reaction than others. And that's what order said. That's what order means. So each reactant can be 0th order, 1st order, or 2nd order. It can be 3rd order, but usually it won't. That's too high for the MCAT. Usually it's 0th order, 1st order, or 2nd order. Okay. Oh, and Janelle is also here in the chat. She is another one of the tutors, if you guys didn't know. Okay. Sorry, I just want to point that out. So each reactant will be 0th order, 1st order, 2nd order, and that corresponds to the exponent you'll see up here, the little a. So if, for example, the reactant is to the 1st order, the exponent will be to the first power, will be a 1. If it's the 2nd order, the exponent will be to the 2nd power, to 2. Okay, and it could be different for each reactant. So for example, in this case, A could be to the 1st order and B could be to the 2nd order, or one of them could be to the 0th order. Okay, and these are the orders of the reaction with respect to that reactant. In addition, there's an order of a reaction overall. This corresponds to the sum of the orders of each reactant. So again, if A was the 1st order, B was the 2nd order, the reaction as a whole will be to the 3rd order because it's 1 plus 2. Okay.
Mark, I'm sorry. You said not to consider intermediates or products. However, when we calculate K, isn't it products over reactants? So why are you telling us not to consider the products?
Okay, so that's something we'll cover later. The K you're thinking of is the equilibrium constant. This is the rate constant. I know it's a little bit confusing, but it's not the same K. They're different constants. This is rate constant, which is different than equilibrium constant, which we'll cover later in the lecture. Okay.
Oh, okay. Thank you.
Yeah, and as a note, I think I mentioned this actually not next to the poll question, but before we do that, I wanted to mention that this A and B have nothing to do with the stoichiometry of the reaction. So for example, if we want to go back to this, so if we were looking at this reaction, the rate, you would think maybe it would be to the 6th power because there's if you were to consider O2, it would be to the 6th power, but it's actually not because stoichiometric coefficients for rate of reactions have no meaning. Okay, this is completely dependent on order. Order is something that the question has to give to you or the passage has to give to you. You can't determine it based on stoichiometry or any other factors. You have to be either given it either like directly or in real life you would have to do an experiment to find out, but the test they would give it to you.
So we're looking at the rate and not K when you said not to consider products and intermediates?
So products and intermediates, so this whole equation, so the equation equals rate, the equation for rate equals the rate constant K, which is always the same for every reaction, times the concentration of each reactant. So if there was like 3 reactants, it would be times A times B times C. If there was 1 reactant, it would be just times A, but you wouldn't consider any products in here, okay?
Okay, thank you.
So however many reactants are, that's how many like letters there'd be A, B, or C.
Okay, you clarified it. Thank you.
Okay, so I just want to get the quick question. This is the first one. As a note, this one's a little bit tricky, so really kind of like think about it, okay? I'll launch the poll. Okay. If you were here last week, you would know that most of these questions that I get aren't ones that I made up. They're ones that I get from actual MCAT prep sources online or in books that I have, okay? So these are real MCAT-like questions. Polls up, if you can guys see the polling. Yeah, I can see a couple of people are getting votes in. Okay. Just want everybody to get again, this one's a little bit tricky, so really read the question, think about it. Okay, I'm gonna give you guys another like 20 seconds to get your answers in, and then I'll stop the poll. Okay, the majority of people voted. Okay, last chance. Okay, so I'm gonna show the results. Okay, so the majority of people put C as the right answer. However, this is actually not the right answer. So, and this is kind of what I expected the answer to be. This is what I thought you guys would say. The correct answer is actually D. The reason is, and I think this is where the confusion came in. So it says the concentration of a reactant in a second order reaction is increased by a factor of 4. How much is the rate altered? So if you guys looked at this equation, you would assume that it would be the concentration of 8 to the second power. If you increased it by 4, if you square it, the rate would increase by a factor of 16, all else being equal. That's actually not the case, because like I mentioned before, there's order of a reaction with respect to each reactant, and there's order of a reaction overall. This question was asking about order of a reaction overall, okay? And that's what it gave you, second order of the reaction overall. This doesn't mean that the order of the reactant that they're talking about is actually to the second order. For example, it could be to the first order, and there could be a second reactant that's also to the first order, which gives you the reaction to the second order. Or this could have been to the 0th order, this reactant, and there could have been another reactant that was second order, and making the whole reaction second order. Therefore, technically A, B, C could have all been correct answers. You can't narrow it down. And because of that, D is the correct answer. Okay? Does that make sense? Does anybody have any questions about that? So like I mentioned, this question is a little bit tricky, and you really had to like kind of read and the specifics of it. All right. Any questions about it?
I have a question.
Go ahead first.
You know how most of us said it's C? Like, how would they put in the questions to get that factor of 16?
So they would say the concentration of a reactant in a second order reaction with respect to the reactant, for example, or something like that. They would say that the reactant itself is to the second order, not the reaction, or the reaction with respect to the reactant. Okay, or they would say that it's the only reactant, for example. If they'd showed you an equation and in that equation you saw that this reactant that they were talking about is the only reactant, for example, that they could do it that way. basically you would have to find out that this is either the only reaction or this reactant specifically is to the second order. Okay. And question before, yes, there's essentially not enough info to say for sure because they just don't give you the full picture. And that's why it can't be determined. Okay. So I want to talk a little bit about equilibrium. So equilibrium, what equilibrium means is that a chemical reaction is perfectly balanced, but not balanced in the sense of stoichiometric balancing like we did before. Balanced in this sense means that the forward and reverse reactions are happening at the same rate, and there is no overall change over time. Okay. So as a note, this doesn't mean that the concentrations of the products and reactants are the same, only that there's no change happening. So I think this could be, with the picture, this would look better. So for example, if we had this equilibrium reaction, and that's what the two arrows going this way mean, there's a forward reaction and then a reverse reaction, they're in equilibrium. As you can see, when you first take N2O4, like pretend it was like cryo-frozen so it can't react, and you put it in a container and then kind of like let it go so it could react, it would change over time. So the concentration of that would start high and there would be no products because it hasn't reacted yet. And then quickly over time, it would shift to the right, it would go the forward reaction, and most of it would turn into NO2, right? Once it reaches a point, which is marked by this dotted line, where equilibrium is achieved, and the system would consider itself, okay, we're perfectly balanced, we don't want to change the concentrations of either anymore, and so it maintains the concentrations as constant unless some outside source is changed. Okay, so like I said, the concentrations, as you can see from this red and blue graph, they're not the same. The concentrations are very different, but that doesn't mean it's not in equilibrium. The system decided that this is balanced. We consider this to be balanced given the situation. Okay, and so it doesn't want to change anymore. So as a note, in both of these graphs, at all times during the whole reaction, there's forward and reverse reactions. There's always, at every point in this graph, N2O4 that's being converted to NO2, but there's also at every point NO2 being converted back to N2O4. The only difference is one of the rates is usually faster than the other, unless you reach at equilibrium, in which case it's the rates are the same in both directions. So if you want to think about it, if you had like a fence and you had two people on either side of the fence and they were throwing balls back and forth, initially one side is throwing balls to the other side faster, and there's more balls being thrown onto that one side, onto side A. But then once you reach equilibrium, both balls across both sides are being thrown at the same rate. So side A is throwing the balls to the other side of the fence at the same rate that the person B is throwing to side A. Okay? Does that kind of make sense, or is that a little bit more confusing?
Do they, since you said they're happening simultaneously, so in the graph, does it eventually go to zero? Like the red curve, it's curving towards the x-axis, which is time. Should I assume that it's going to eventually go to zero, time-wise, completion?
So no. So initially, the concentration of the blue line is like the initial concentration of the reactant, like what you started with, and the initial concentration of the product is zero because there's no product. The reaction hasn't started yet, essentially. Once the reaction starts, then it speeds up. It will never go to zero because, as you see, once you get past this dotted line, equilibrium achieved, the lines will always be straight lines. They'll never move. Like unless something outside acts on them, they'll always be like perfectly straight and like into infinity. Okay, because they've reached equilibrium. They're not going to change ever again. Okay, so the only reason that
means forever, but a reaction doesn't go on forever. You know, you're saying that it goes
so
to.
So actually, so if you left it alone, a system would at equilibrium would pretty much go on forever. So if you want to think of it like in like a lake right now in the world, there's reactions going on like forever. Like they're constantly shifting like this way, that way. They're just at equilibrium, so you don't notice the changes, but that doesn't mean they're not happening. So just because you don't notice chemical reactions that are happening, because at equilibrium you won't notice anything, right? Because there's no change over time net. There's no net change over time.
All right.
But
Okay.
on a minuscule level, there's always changes. It's just
Okay.
that they're in both directions at the same time. Okay.
Right. Thank you.
Yeah. So, and as I mentioned before the dotted line, the only reason the concentrations are changing is because they want to reach that equilibrium point where they're no longer changing. The system will always try and reach equilibrium, no matter what it is. Okay. So you mentioned this before, actually, the equilibrium constant, which is written as KEQ. Okay. It's also written as K, but it's completely different from the rate constant. It's fairly different from the rate constant in that it's the way you get it is completely different, and what it signifies is completely different. The concept is the same as the rate constant. Each reaction has its own equilibrium constant. So, for example, this reaction N2O4 to NO2, it would have its own equilibrium constant that is true for every single reaction N2O4 to N2O2, except when temperature changes, because the only thing that could change equilibrium constant is temperature. If you raise the temperature, equilibrium constant changes. If you lower temperature, equilibrium constant changes. Otherwise, the equilibrium constant for a certain reaction at a given temperature never changes. Okay. And this will be important later on, and we'll come back to it. Okay. Using the equilibrium constant, you can determine which way that the reaction will favor, whether it will favor the product or the reactants. So again, as you can see in here, this reaction based on this graph favors the products, because when it reaches equilibrium, there's more products than there are reactants. Okay, so that's what we mean by it favors the products. Okay. Yes, I'm going to send the slides and the link to the recording later.
What did you say about temperature? What did you say about temperature is the only thing? What?
Temperature is the only thing that could change equilibrium constant. So even for this reaction, this equilibrium reaction, the equilibrium constant for this reaction at, like, say 25 degrees Celsius is always the same no matter what other conditions are changed. However, at 28 degrees Celsius, the equilibrium constant for this reaction is different. So temperature does change equilibrium constant. You don't have to know exactly how it changed it, because I don't believe that's part of the MCAT. That's like more of an advanced like chemistry topic. Exactly how it changes, and so you don't really have to know that, I don't think. But just know that like temperature is the only thing that could change equilibrium constant. Okay. All right. Equilibrium constants are values. They can be very extreme. So they can range from something like 10 to the negative 15th to 10 to the 15th. They could even be lower or higher than that. They could be to the negative 30th or to the 10 to the 30th. They could be huge or very, very tiny. Okay. The larger the equilibrium constant is, the more it favors the reaction to the right. And the smaller it is, the more it favors the reaction to the left. So if you had an equilibrium constant of 10 to the 30th, that means you're going to have way, way, way more products at equilibrium. You'll have way, way, way more products than you will have reactants. And if it's super small, like 10 to the negative 30th, you'll have way, way more reactants than you will have products at the equilibrium. Okay, and it can range from anywhere from these values. Okay, here at the bottom you see the equilibrium constant, and this is what Opal, you mentioned earlier, concentration of products over reactants. Okay. So you see that concentration of NO2, which is the product in this equilibrium, is at top, and concentration of reactants is on the bottom. And in this case, unlike with the rate constant, the exponent is actually the stoichiometric coefficient. The way you can think of that is, if you were to write an equilibrium constant using just like all the products of all the reactants, and there's two different NO2s that are made, two different molecules of NO2. So you would have NO2 times NO2 over N2O4, but you can simplify that to NO2 squared, okay? Okay, I'll cover that again, what I mean it favors to the reaction to the right. So you see how in this N2O4 to NO2, this reaction, it can go to the right or to the left. Favors to the right means, okay, go back to this. So you see, this is the graph for this reaction, for this equilibrium reaction, and this graph is concentration over time, right? So the y-axis represents the concentration. You see when it reaches equilibrium, past this dotted line, the concentrations don't change, but the concentrations between the products and the reactants are not equal. If the concentration of the product is greater than the concentration of the reactant, we say that it favors it to the right. It favors the reaction to the right because the arrow pointing to the right is the main reaction. Okay, so if it favors to the right, more NO2 is made because more of the right reaction is happening. Okay, whereas if it favors to the left, this graph would be flipped, and there would be more N2O4 at equilibrium. The concentration would be higher than NO2, and we say the arrow pointing to the left would be kind of like the main reaction. Okay, so it's favors to the right or favors to the left is based on whether the concentration of products or reactants at equilibrium is more pronounced or kind of higher. Okay, and we were mentioning equilibrium constant. If it's small, it favors it to the left, and we can see based on this equation, the products over reactants, why that makes sense. So for example, if you had 10 to the equilibrium constant 10 to the negative 15, this KQ equals 10 to the negative 15th. That means you know that whatever's on top, this concentration on top has to be much, much lower than what this concentration on the bottom is, right? So, and that's how you could kind of see, at equilibrium, there's much less product than there is reactant. That's why the equilibrium constant is so small, okay? So if this is 10 to the negative 15th, means the top part must be much smaller than the bottom part, and you can kind of think of it that way. And if it was huge, like 10 to the 15th, the opposite. The top part would be much, the ratio of the top part to the bottom part would have to be massive. So that means there'll be more products or this top value, okay? Is this clear, or is there any questions? Sorry. Any questions, or is kind of clear? Okay. Let's move on. So another clicker question. Okay, I opened up the poll. Can everybody see it? Okay, cool. So get your answers in. Yes, I'll explain this question afterwards, of course. Yeah, just with these quick questions, just try your best, kind of, and I'll of course explain it afterwards. Make sure everybody understands. Okay, yeah, no problem. I'll cover this once we get more people voted in. Another minute or so for voting. Kind of like a useful hint on the MCAT, if you really don't know a question, kind of try and eliminate as many answer choices as you can. Kind of at that point, yes. but I'm going to try and make sure that you guys understand this topic enough so that you don't have to on the MCAT. Okay, get your answers in. I'm about to close the poll. All right. Okay. Okay, closing out. So as you guys can see, most people went with C, 45%. And then a couple people went with A and B. So that's good. Most people did get the right answer. The answer is C. I can explain why. So if you notice, reaction 1 and reaction 2 are the exact same reaction, except just reversed. If you notice, and they're both at equilibrium, right? So that essentially they're the same reaction. So we know that the KEQ for the reaction 1, so this one is 0.1, and we want to find out what it is for reaction 2, right? Since we know that reaction 2 is just the reverse of reaction 1, in this case, the products, so KQ is products over reactants, if you want to think about it that way mathematically. KQ is products over reactants. For reaction 1, the products over reactants is equal to 0.1. Whereas for reaction 2, doing products over reactants is just flipped of what it is for reaction 1. So if you want to think about it that way, it's just for reaction 2, the KQ is just 1 over what it was for reaction 1. 1 over 0.1 is 10. It's just inverted. It's just flipped. So since the forward reaction for this one is 0.1, the reverse is 10. Yeah, and Janelle posted in the chat kind of like a little bit more of what I said. Yeah, like if you are a little bit confused, read what you said and maybe it'll help. But essentially, because they're the same reaction, just flipped, the KEQs for them would be the same, just flipped, like inverted. So from 0.1, you know, is 1 over 10. So if you inverted it, it would just be 10 over 1, which is 10. Okay. And it seems that most of you got that. Some of you were a little bit confused, and that's okay. It wouldn't be A because, again, it's a reverse reaction. So it's like flipped reaction. So it couldn't be the same. 1, equilibrium, it wouldn't be unless for reaction 1, if it was 1, then for reaction 2, it would also be 1. In that case, it would be the same. What that means is that at equilibrium, there's a perfect balance of reactants to products. They're exactly the same. So products over reactants would be 1, which means that they're both equal values, equal numbers. Okay. Is that kind of clear, or people were confused? Are you guys still confused, or? In reaction 1, there's 4D is not equal to reactants. Okay. So here I can maybe here clarify that. So you see that these, first thing you have to notice that these reactions are the same, just opposite. So it's 3A plus 2B goes into 3C plus 4D, whereas here it goes 4D plus 3C, which is just this, goes into 3A plus 2B. Okay. So if we're looking at reaction 1, how did we determine that what does the KQ of 0.1 mean? So if we go back, so if this is equal to 0.1, this KQ value is 0.1, that means the products to the reactants was in a ratio of 1 of the products to 10 reactants. There's 10 times more products, 10 times more reactants, I'm sorry, 10 times more reactants here on the bottom than there were products here on the top. That's why you got a value of 1 over 10, which is equal to 0.1. And that's how you got the KQ of 0.1. Well, if you look at here, if you flipped it, and now the reactants are the products, and the products are now the reactants, if you just switched what the products and reactants are in order-wise, now, since you know there was 10 times more of C and D than there was A and B in this one, there's 10 times more. So again, KQ is 0.1. That means there's 10 times more reactants to this A and B than there was C and D. So if you reverse the reaction, nothing has changed. There's still 10 times more A and B than there is C and D, except now it's products over reactants 10 over 1 rather than 1 over 10. Okay? Yes. Yeah. Okay. Is that clear? So think of it this way, that if 0.1, 10 times more reactants than products, 10 times more A and B than C and D. Here, there's 10 times more A and B over C and D, so products over reactants will be 10 over 1. Okay. Next up, we're talking about Le Chatelier's principle. So this states that equilibriums do shift in response to external conditions. Like I mentioned, KEQ does not change except for temperature, right? But for example, if more molecules are put in, the equilibrium will shift in the opposite direction to balance out. And here I can go back and show this to you based on this equation, right? So you know that no matter what, KEQ cannot change, right? But if, for example, you have a certain ratio, say NO2 to N2O4, say again, we'll go the 10 to 1 ratio, 10 times more NO2 than there is N2O4, and the KEQ is 10. I told you that the KEQ cannot change. So for example, if you put in more N2O4 concentration as the reaction was happening, you just funneled in more N2O4 of this reactant, this would go up. If this went up, say it doubled, it would no longer be a 10 to 1 ratio. It would now be a 10 to 2 ratio or a 5 to 1 ratio. This would change KEQ, which is not allowed, right? So in order to prevent that and to keep the ratio the same, what you have to do is you have to make more NO2. You have to convert more of this to NO2, right? If you want to think about it that way, you have to convert. If you put in more reactants to maintain the ratio, you have to convert more of the reactant to the product, right? Similarly, if you had the same thing, a 10 to 1 ratio, but as the product was being made in like a container in the test tube, you like vacuumed it out, like took out product as it was being made. This would lower this to, say again, 5 to 1 ratio. That would change KEQ, which again is not allowed. So you would have to convert more of this to this. This would lower this. This would lower the ratio by. This would make the ratio back to what it originally was by lowering this value and increasing this value to balance out. Okay. Thus keeping KEQ the same. So if you take out the product, then you would shift to the right. You would convert more of this reactant to more product. If you add in more reactant, more of the reactant would also shift to the right to make more product. Okay. And that's if we're talking about concentrations. Another thing about Le Chatelier's principle and KEQ in general is it doesn't necessarily have to be based on concentration. If we're talking about gases, it could also technically be partial pressure of gases. So instead of concentration of NO2 and concentration of N2O4, instead you could use partial pressure of NO2 and partial pressure of N2O4. We haven't covered partial pressure yet, and we will when we do physics much later. But essentially, partial pressure, you know that pressure is made up by gases. Without gases, there's not pressure, right? So if you and each gas contributes something to the pressure. Partial pressure is how much contribution each gas contributes to the total pressure. Think of it like, what percentage of the total pressure is due to this one gas? And that's what the partial pressure is. That's essentially what it is. Okay, and this only applies to gases, solids and liquids and anything else. They don't have partial pressures, right? So if you had partial pressures, it would be the exact same thing. KEQ, partial pressure of NO2 squared, because you still keep stoichiometric coefficients, over partial pressure of N2O4. The KEQs for partial pressure, KEQ for concentrations should be about the same, right? Because KEQ again doesn't change, and KEQ is a unitless constant, so it doesn't matter what the units were of what you did before. Partial pressure has different units, and concentration, but they cancel out because KQ has no units, right? So it doesn't matter if it was originally partial pressure or if it was originally concentration or whatever, right? If you had partial pressures, the same thing would apply. So if you had partial pressure squared over partial pressure of this, and as a result, if you change the pressure one way or the other, it would also change the KQ. It should change the KQ, but again, that doesn't happen. And as a result, like to not change the the KQ, you would have to shift either left or right. The way you do this is whichever side has more gas molecules, that's the side to which equilibrium goes away from. So here, I'll actually yes, I don't want to give that too much away because I want you to actually think about it by yourselves and see if you can solve this question first, because I don't want to give the answer away yet right now. I want you to at least like think about it a little bit, and then I'll make sure to go over it. And for this one, remember the ideal gas law, which I will put in chat actually. There you go. P is pressure, V is volume, N is moles, R is a constant, T is temperature. So that's kind of a hint. Ideal gas law is important for this question. Think about it. Why did I give you the ideal gas law? Yeah, look at the relationship between some of the variables. How would changing one variable affect another? Maybe think about that. You can't see the poll? Can you see the poll, Opal?
Yeah, I just saw it. Thank you. I got it.
Yeah. Wow. Okay. I'll give you guys another minute or two because this is a little bit complicated one, and I didn't really go over this that much yet. I will after. I promise I will after the poll. I'll be more clear. As a hint, try and think about another hint. Try and think about the ratio using partial pressures, because you don't have concentrations this one, so it must be partial pressures. So think about how the ratio normally is and how it would change based on how you change the answers. Okay.
We should have made this on Roman numeral like A and 2 and 1. Those are the ones that messes me up. Right? They say 1 and 2 is correct, 2 and 3, those.
Okay. 10 more seconds if you don't know, try and get your answers in. Give your best guess. Okay. I'm about to close the poll and okay. So the most popular answers were C and D, but it was very, very fairly split between all four answers, which is what I expected. The correct answer is A. So let's think about why that is. So as I mentioned, partial pressures, this question is based on partial pressures and moving the equilibrium to the right, shifting the equilibrium to the right, okay? So we know that the only gas here is this iodine, right? So that would be a very low value because the products basically have no partial pressure. So it would be extremely low value over a relatively much larger value because partial pressure of gas is much, much, much higher than liquid, solids, aqueous solutions, and anything else. Okay, so it would be the equilibrium constant would be fairly small. So how do we kind of make the equilibrium go to the right? Well, if you decrease the volume, if you look back at the ideal gas law, where PV equals nRT, this must always be true. PV equals nRT, right? We're not changing the moles. We're not changing the constant. Constant doesn't change R. And we're not changing T because there's no mention of temperature or moles or anything changing, right? So the only things that do change are pressure and volume. If you decrease the volume, the pressure must go up in order to balance it. Because if the right side doesn't change, you change one of the variables on the left side, the other variable on the left side must go up in order to kind of balance it out, right? To keep the value equal, to keep the equation true. If you increase the volume, if you increase the pressure, so what happens is it will favor more, it will try and kind of keep the KQ constant. So it'll shift more towards the side that has a lower partial pressure. The way you know which side has lower partial pressure, the side that has lower gases, right? The less number of moles of gas. Since this one has 1 mole of gas, this one has no moles of gas, it would shift to the right. And that would keep the equation true because if otherwise, the I in the bottom would go up. The partial pressure of the I on the bottom would go up if you increase the pressure, but the top wouldn't change. And that would kind of break the KQ. In order to balance that, you have to send some of the I to the product side to kind of keep the ratio the same, right? It's the same idea as with concentrations. If you increase the concentration of I instead of the pressure, you would also realize that it would shift it to the right. Same thing with pressure. If you increase the pressure of I, it would still shift it to the right. Sometimes when there's multiple gases, so for example, if this FEI was also gas form and this FEI 3 was also gas form, you would have 2 moles of gas on the left and 1 mole of gas on the right. It would still shift to the right because more gas on the left, it would increase the partial pressure more relative to the right side, and you would shift to the right again. If there were more moles of gas on the right side than on the left, it would shift to the left.
No, why be incorrect? Because it's also saying decrease in the volume.
Decreasing the volume while maintaining constant pressure, it's wrong because that wouldn't change the equilibrium. Volume doesn't actually change equilibrium. The reason like decreasing volume is like the right answer because normally decreasing volume, unless otherwise stated, would increase the pressure, and that's what changes it. It's not changing volume doesn't change equilibrium constant. Only changing pressure would change the equilibrium constant, right? So since this this answer says we're decreasing the volume while maintaining constant pressure, you don't really know what it would do because that means you would have to change either you'd most likely have to change the temperature, and you don't really know how that would kind of affect the equation, right? You don't have all the information for that. like I mentioned, it's more complicated when you change pressure, how it affects KEQ, right? So decreasing volume while maintaining constant pressure doesn't actually do anything. It would do something if you change T, but you don't know what that is. Whereas decreasing the volume by changing and also changing pressure, which is kind of implied, would change in the correct way. Decreasing the pressure of the container B is also wrong because that would actually have the opposite effect. Decreasing the pressure would shift more to the left because it would shift towards the side that has more moles of gas, which is the left. Is this clear? Oh, sorry, skipped a lot. Is this clear, or do you want me to explain again? I know this is a little bit confusing. This is kind of a hard topic, yeah. Any questions in the chat, or anybody want to ask? Okay, if not, I'll move on. Okay, I can explain again, yeah. So, let's just remember this. I'm gonna go back to this just because it gives a clearer picture, like the KEQ equation. So if you replace this concentration with partial pressure, which is what the question was kind of asking you to do, you would notice that it would be partial pressure of the products over partial pressure of the reactants. The partial pressure of the products is very, 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 very small because solids, liquids, aqueous solutions, anything that's not a gas has basically no partial pressure. Whereas gases have an actual like pretty high partial pressure relative. So it would be, so the ratio of products over reactants would be very, very, very like small. It would be like probably like the equilibrium constant would be like to the -30th or something like that. It would be very, very, very small. What happens when you increase pressure? Well, when you increase pressure, the partial pressure of the bottom would increase, whereas the partial pressure of the sorry.
I'm sorry. I'm a mute.
No problem. Whereas the partial pressure of the top will not change because with aqueous solutions, liquids, solids, it doesn't change with pressure. The partial pressure doesn't really change with pressure. Whereas with gases, it heavily does. So that would increase the bottom, just like in this situation, increasing the concentration would shift the equilibrium. Increasing the partial pressure of the gas would normally change the equilibrium constant by making it actually even smaller. Since you don't want to do that, you would have to actually move away from the reactants to the product in order to keep the ratio of equilibrium constant the same, right? So if you want to even think about it in concentrations, if you increase the value of the concentration of the reactants, it would shift to the right to make more products to keep the equilibrium constant the same. The same thing with partial pressure in gases. Increase the pressure, that increases the partial pressure of the gases. That would normally increase the value of this bottom part. To balance out, you have to shift some of it to the top, to the right side, to the product side. The way we know that the pressure increases is PV equals nRT. You know nRT pretty much normally doesn't change. So if you have the same value on the right side and you increase and you decrease one of the values on the left side, in order to make the equation still hold true so that the left side equals the right side, you have to increase the other value on the left side, which is pressure. Okay. You can also think of it that way. If you decrease the volume, obviously like the pressure would increase. Like if you had a gas over a big area, there's low pressure because it can kind of like move around freely. If you decrease the volume a lot to like kind of condense it, it would kind of be like a lot more pressurized. That's kind of the basic principle. Kind of like if you want to think about it, kind of like even in your like everyday life, natural life. Yeah. Boyle's law also works as she mentioned here. Yeah, the only way that Boyle's law, it doesn't exactly work is for D, which decreases the volume while maintaining constant pressure. Normally, pressure increases when volume decreases, but if you're being told that it's being maintained constant, that means you have to be changing something else, either on the right side, and you can't change R, and you wouldn't really be changing T would be the only thing you would really change, which you don't know how that would affect the equilibrium constant because you don't have enough information from this question. Yeah, so is that more clear, or? So your main goal is to find out how could you increase the pressure. Well, once you figure out that increase in pressure would shift the equilibrium to the right, you would have to find out how can we increase pressure. The only way to do that is by decreasing the volume. Is that clear? Any other questions? Or would you like me to explain it again? Oh, of which part favors which part? So do you understand the basic idea with concentration? Because that seems like more people like usually have better understanding of concentration than they do of partial pressures. If I increase the concentration of I2 of the gas, if I increase its concentration, do you understand why it would shift to the right? Niyusha, do you understand why it would shift to the right to kind of balance out? Do you understand that part? If I just increase the concentration of the gas, of the I2 gas.
Kind of.
Okay. Well, the way you want to think about it is increasing pressure is the same as increasing concentration for gas. They're like equivalent, because equilibrium constant can apply to pressure or to concentration. So increasing the pressure of a gas also is equivalent to increasing concentration. So when they say what effect would increasing pressure have on this, you could basically substitute increasing pressure with increasing concentration for all gases, like uniformly. Since this is the only gas, this is the only thing that actually gets increased when you increase pressure. If you had more gases, they would all uniformly get increased, actually. Okay, does that make sense?
Yeah, kind of.
Okay,
Thank
so just like if you increase concentration, it would shift to the right. Increasing pressure would shift it to the right. The reason it would shift, the reason it would shift concentration is, again, I'm going to talk about this. This ratio. Think of equilibrium constant as a ratio, always a ratio of product to reactants. If you have a certain ratio, say 10 to 1, products to reactants, the equilibrium constant is 10 to 1, which is 10. If you were to artificially increase something by either adding in concentration or taking away, it would change the ratio. It would go from 10 to 1 to maybe 5 to 1. And that would change the equilibrium constant to 5. You can't change the equilibrium constant. I mentioned this. There's no way to change the equilibrium constant. So the system itself would kind of balance it so that the equilibrium constant doesn't change, right? Well, the way it balances is, and you can think about it this way. So if you were to change, if it was a product, it was a ratio of 10 to 1 products, 10 to 1 reactants, and you took away the products as they were being made, you took them away out of the system, it would shift down to 5/1, right? Well, it can't do that. So what does it want to do? It wants to take some of the reactants, some of the 1, and actually give it up to make more products. So it wants to give up the reactants and make more products to kind of balance out. That what that would do is it would decrease the concentration of the reactants and also increase the concentration of the products. But if you were to convert more reactants into products, that would then slowly kind of remake the ratio of 10 to 1 that it wants to keep, right? Does that make sense?
Yeah. Okay, thank you.
No problem, yeah. Yeah, so just think of it like very, very generally. Whichever side you're adding to, that's the side that's going to have to kind of give stuff away to the other side. If you're taking away from a side, it's going to receive from the other side. Okay. All right. In equilibrium, there are, now we want to get back into how equilibrium relates to rates, okay? Because we talked about equilibrium and we talked about rates. In equilibrium, there are 2 reactions with 2 different K values, right? But the rates should be at equilibrium. So like we mentioned before, rate equals equilibrium constant K times the concentration of the reactants, right? Well, in an equilibrium reaction, I mentioned at equilibrium, the rates of the forward and reverse reaction are equal. And that's why there's no net change over time, because the rate this way and the rate this way are both the same. But that doesn't mean the equations for the rates of each one are the same, right? So each direction has its own rate constant, K1 and a K-1. K1 is of this forward reaction, K-1 is of this reverse reaction, and that's the rate constant, right? They also have different equations. So this left one has a rate reaction of rate equals K1, its equilibrium constant, times its reactants, which in this case, this is the reactant, to the order, whichever order it is. The reverse reaction has a rate of K-1, its rate constant, times NO2, which is, in this case, which is its reactant, because this reaction, this is the reactant, this is the product, right? But you know that this rate equals this rate. So K1 times concentration N2O4 equals K-1 concentration of NO2. You know that these are actually equal, right? Okay. Next up, we want to talk about rate determining step. Okay. Most reactions don't proceed in one step, like you just have reactant magically gets converted into product. Usually there's multiple steps. So for example, here I outlined something. A plus B plus C goes into ABC. That's like the overall reaction, but it doesn't happen in one step. It happens in two steps. First, you take A and B, you combine them, you make AB. Then you take AB, you add in C, you make ABC. You'll notice that there's a slow and a fast. This represents how quickly the reactions happen. This reaction, A plus B goes to AB, happens very slowly, relatively slowly, whereas AB plus C to ABC happens much faster than this one. Well, what happens when you have a slow step and a fast step? How does that affect the rate? Well, the rate is really only determined of the whole reaction of the slowest step of the reaction, right? So if you want to think about it, this takes a long time to make, and this is very fast. So the rate of the whole thing is really only dependent on the rate of the slow step. So if you want to think about it kind of like if you're cooking, if maybe chopping things up and getting everything ready takes like maybe 2 minutes, but then cooking, like actually putting something in the oven and then cooking it takes like 3.5 hours. Compared to the 2 minutes, 3.5 hours is a really long time. And when somebody asks you, how long does it take to cook this dish? You would say 3.5 hours, because that's the time it takes to really do the slow step, which is actually like the roasting or the cooking or whatever, right? The rate of the whole process is determined pretty much solely based on the rate of the slowest step. And slow and fast, don't think of it as like the difference between like 10 minutes and 1 minute. Think of it as the difference of like 3 hours and like 2 minutes, right? You really want to, like, the difference between the slow and fast step is a big, big, big. Okay. The rate determining step is always the slowest step. So that's what determines the rate, the slowest step. The rate of a multi-step reaction is always equal to the rate of the slowest step, right? So in this case, step 1, which is this step, the red one, is the slowest. So the rate of the whole reaction is basically equal just to this rate. And the rate is equal to K1, because it will be the rate constant of this times the concentration of A times the concentration of B with their respective orders. If instead the slow step was the second one, this is the fast step, this is the slow step, then the rate constant instead would be actually, this should say K2, a concentration of AB, which is the new reactant, and C, which is this reactant, right? However, if step 2 is the slow step, you notice that this thing, AB, or I'll give it a specific example, NO2 to NO, converting NO to NO molecules to NO2, which this has a fast step and this has a slow step. You notice that there's this intermediate, N2O2, which doesn't appear at the beginning and doesn't appear in the end. So if you were to write the overall reaction, like with this blue one, A plus B plus C equals ABC, you would never write AB. like this is an intermediate, and it doesn't appear in this overall reaction. Because of that, when we write a rate law, we can never include the concentration of the intermediate in the rate law, right? So like I mentioned, normally, if step 2 is a slow step, it would be, again, this is supposed to be K2 here. Let's see if I can fix this. Okay, so it would actually be K2. This would actually be K2. I don't want to fix it. My cause errors, but I will fix it when I give out the PowerPoint to you guys. This should be K2, this one, times the concentration of N2O2 O2. Right? This would be the rate law. If this was a slow step, this would be the rate law of the whole equation. But like I mentioned, we don't know what the concentration of N2O2 is, and it's an intermediate, so it doesn't appear in the rate law. You can't use it. However, we have this equation, right? It's an equilibrium. And we have certain things that we know about equilibriums. For example, we know that the rate of this forward reaction equals the rate of this reverse reaction, right? And because of that, we can say K1 times NO squared, because there's I know it's not supposed to be moles, but because there's concentration of NO, there's 2 of them when you're doing this rate law, it actually is squared, right? Because there's 2 different NOs, right? And it's equal to K-1 times the concentration of this, because as I mentioned, equilibrium rates forward and backwards are equal, right? Because we know this, we can now solve for concentration of NO2. We know what concentration of N2O2 is equal to, because we can just divide both sides by K-1, right? If we divide both sides by K-1, we isolate NO2, and we know that concentration of N2O2 is equal to this, right? K1 times concentration of NO squared over K-1. Now we can take this original rate law for step 2, which had the concentration of N2O2, and we can just substitute in this big thing for N2O2, since we know they're equal, right? So rate equals K, this should actually be K2, and this should be, this should be K2, and this should be K-1. I'm confused, but I will make sure that they are corrected for the PowerPoints, right? So this is K2 times K1 over NO2 over K-1. So we just took this thing, put it in these parentheses over here. Then we took K2, which here it should be K2 as well, K2, and then we multiplied it by the other reactant, which is O2, right? Does that make sense, actually? Before we continue, does that make sense? So I know this is a little bit of, there's a lot of math, a lot of equations and stuff, but could you guys follow? All you simply did was you took something you knew about equations, which is that about equilibriums, which is that both rates are equal, and rates, the rate laws for each one would be written as this. And then you could just simplify and solve for what concentration of N2O2 is, and then you could substitute it in for the slow step, and you could find out what the slow step is, the rate of the slow step. Does that make sense? Yes, okay. Moving on. We're actually wrapping up. We're getting close to being finished. Okay. Next, we want to talk about activation energy and curves. This involves a little bit of thermodynamics, right? Which we haven't covered yet, but I'll try and explain it very briefly. The x-axis in this graph represents the progression of the reaction from start to finish. So here, where it's a straight line to start, this is what the reactants look like. This is where it's still in its reactant form. This, at the end, the straight line, is its product form. This is what the products are like. These curves in the middle are the actual reaction, the progress of the reaction. If you notice, there's kind of like a small straight line right here in the middle in between the two mountains. This is the intermediates. As you notice, it's supposed to be a straight line just like the reactants and products, but it's just so short. It lasts for such a short time that you can't even really see that it's a straight line. That's because intermediates are very unstable. And as soon as you get to the intermediate form, you'll pretty much almost always just go straight to the end. You won't stay in that form for very long like you would in the reactant or the product form. The most important part of this graph is, however, this little first bump and this second bump, right? These are called activation energies. So there's this thing called potential energy or Gibbs free energy. This is basically the energy that a certain molecule, like a compound, has, right? Ideally, in nature, everything wants to go to its lowest possible energy form. So as you can see here, this has a high energy because it's higher up on the graph, like on the y-axis. It has higher energy, the reactants, than the product. The products have a lower energy, potential energy, Gibbs free energy. That means it's actually favorable for the reactants to be converted into products. Nature wants this to happen. And it happens spontaneously. So that means humans don't have to interfere. You don't have to have any outside sources that interfere. This will just happen in nature spontaneously without any outside interference, right? Because this is the way nature wants to go, from high energy to low energy, right? However, there are these hills called activation energies. These hills, as you can see, they require a large spike in energy, and they're kind of like guardians, think of the reaction. They're what like stop the reaction from happening. They're like literally mountains that the reactants have to cross in order to get to the other side where they want to be, right? These activation energies can be really big, as you can see with this one, this first one, or they can be small, like you can see from intermediates to products. The second step of the reaction is very small. The bigger the activation energy, the longer the reaction takes. So this reaction will pretty much almost always occur. How fast it'll occur, that depends on the activation energy. So if this activation energy is really big, this reaction could take actually years to occur. It will occur, but it'll just take years because the activation energy is so big. However, once, like I mentioned, this would, if we're talking about rate determining step, this is the slow step because this has a huge activation energy. Once this gets converted into the intermediate is very unstable. The activation energy is very small. It just immediately goes to the product, but very fast, right? So how do we use this information to kind of help us for our chemical reactions when we're working in a lab or in whatever? Well, we have something called catalysts. Catalysts are compounds that appear at the beginning of a reaction and at the end of the reaction, and they're unchanged. They don't actually undergo any change themselves, but they're very important. They fulfill a very important function. They increase the rate of the reaction. An uncatalyzed reaction could take years to happen. With a catalyst, it could take minutes. It can be that extreme, right? It allows reactions that are thermodynamically favorable to occur quicker. Like I mentioned, certain reactions are favorable and they will happen, but they'll take years. With a catalyst, it can speed it up to take minutes. The way they do this is they lower the activation energy required to initiate reaction, okay? Okay, so this graph is a perfect example of that. So in this, we're just having a one-step reaction. Again, look, reactants, products. You can see it's thermodynamically favorable because the reactants have more energy than the products, so they want to go to that lower energy state. In blue is the activation energy without a catalyst. You can see it's a huge cliff. It would be very difficult for these reactants to actually overcome this cliff and go to the products. However, if you introduce a catalyst, it will lower the size of the hill that it has to cross. And now this will happen much easier, much faster. Okay? Catalysts, in the way you can identify a catalyst is, if we go back to any equation, for example, with this one, you can see you start off with 2 NO molecules and you end with 2 NO2 molecules, right? So this is the reactants, these are the products. If, for example, in addition to these 2 NO molecules, you had, say, an enzyme. Imagine this was happening inside of bacteria and you had a enzyme called like nitrate synthase or whatever, some random enzyme that the bacteria has. And remember, all enzymes are catalysts. That's the purpose of an enzyme. It's a biological catalyst. So all enzymes are essentially just catalysts that speed up reactions that happen in our body. So if you had, in addition to these two NOs right here, you had a nitrate synthase, this enzyme, this catalyst, it would speed up this reaction. It might speed up this reaction as well, depending on what it's a catalyst for. And then at the end, you would still have 2NO2, and then you would have the enzyme or the catalyst, nitrate synthase. And that's how you know it's a catalyst, because it would appear at the beginning, the very beginning of the reaction, nitrate synthase, and then it would appear at the very end, nitrate synthase, and it would be completely unchanged. It would end exactly how it started, no change at all, while the rest of the reaction occurred. Obviously, if you put a bunch of things in there and they don't react at all, they're not catalysts. But if there is a reaction that happens and something in that reaction doesn't change from start to finish, then it's a catalyst. You know for sure it is, if a reaction occurs. Right? And that's how you would know, that's how you would be able to identify if they gave you a reaction. If you see a reaction happen and there's one molecule that's at the very start and at the very end, and it's completely unchanged, it has to be a catalyst that speeds up the reaction. Okay.
So in that example, which one is a catalyst?
So for example, and this one doesn't, this picture doesn't have catalyst. I just said,
Okay.
imagine that there is an enzyme, and I mentioned enzymes are catalysts. That's their job in a biological system. There's in addition to these two NOs, there was another like catalyst that you added in, right? It's called nitrate synthase, and it would appear at the beginning and at the end, unchanged.
Got it.
However, actually, as a quick note, catalysts don't have to remain unchanged throughout the whole reaction, by the way. So for example, if they were to come at the start of step 2, nitrate synthase could be bound to something. It could be slightly altered. The most important thing is that at the end, it's unchanged. But in the middle, it could be changed, right? Catalysts, that's how they work. Sometimes they get changed in the middle, and then at the end, they are the same as they started. Yeah, okay. This I mentioned. Do you have anybody have any questions about catalysts, activation energies, thermodynamics, anything like that before I continue? Enzymes, anything?
What if the energy for the product is higher than the reactant? Does it still happen? The reaction still happens?
No. Naturally, no. That would mean if the energy of the product is higher than reactant, and we'll cover this much more in depth when we cover thermodynamics in a couple of weeks, but the reaction will not happen naturally, it will not occur spontaneously. You would have to do like either a human or like something has to do something special with it in order to make it favorable. So some examples of what would be, you could couple, that's usually what our bodies do inside. Reactions that aren't favorable, they like couple. They take a reaction that is very favorable, that has a big like gap like this between the reactants and products, like a favorable gap, and then they just make sure that the two reactions happen at the same time, and then the overall favorability of the two reactions together would still be favorable. Or you could just put an energy, of course, into the system. Like that's also what we use. Like if you put in ATP, or like if you give it energy to the system, it'll happen. But yeah, no, not naturally. If the products have higher energy than reactants, it will never happen like naturally without some kind of interference.
Got it. Thank you.
Yeah. And by the way, catalysts can also catalyze reactions that don't happen favorably, like I mentioned. Like if you were to couple two different reactions together, there could be a catalyst that could help. Like thermodynamically favorable in this slide, when I mentioned thermodynamically favorable, it allows reactions that are thermodynamically favorable to occur quicker. This doesn't mean necessarily always this. This is in a natural system, but if you put in enough energy into a reaction that's not normally spontaneous, that has the higher energy products than reactants, you can still use a catalyst, because even if you put in energy, that reaction might still take years. Even if you naturally put in energy, or you yourself put in energy, might still take years. So you would still might need a catalyst. Okay. Now, this should be a relatively straightforward question. So let's see if I can Open this up, launch polling. Okay. Okay, I'll give another 30 seconds because it seems like almost everybody's gotten it in. So if you haven't, please do. Okay, I'm going to end the poll right about now. Okay. So very good. Actually, the majority of people got it right. And I just wanted to quickly touch on why A was wrong. It's like I mentioned, it says catalysts are used up in the reaction, increasing reaction efficiency. They do increase reaction efficiency if you want to think about it that way. Catalysts are not used up in the reaction. Like I mentioned, catalysts always have to be there in the start and at the end completely unchanged. So they can't be used up because they have to appear in the end unchanged, right? And then you guys can just C and D are wrong. Bring the transition state to a higher energy, and D would obviously be wrong. That would actually slow down the reaction. Catalysts alter thermodynamics, the reaction formation of products reactants. They don't do that. This is actually an important question, like a thing. They don't change the thermodynamics of, they don't change the energy levels of the reactants or products. That's a question that they love to ask on the MCAT. Only this middle part, this curve, they don't change the value of the reactants or products on the line. They will not, they can't make it go up or down. It is what it is. Like you can't change it with catalysts. So we can, I will talk to Tim about it more because he's really in charge of that. I think he mentioned more on like the Facebook group he puts it on, and on the YouTube channel and other sources, like Socratic Med pages. I was thinking about making this. By the way, this is the last slide. So we can have some conversations now. I was thinking about making like maybe like a group meet chat, or maybe a some other kind of group chat, like maybe Google Meets or something like that, where I would post the link to the lecture recordings and the PowerPoints after every week, and everybody who wants can join in and be there in one place. Oh, sure, go ahead. Yeah. So I was thinking about that. We might get that. We might get that for next week. I'll be sure to do that. If you don't find it on the Socratic Med pages, or you can't find it, please just always email me. I'd be happy to just send it to you by email or by Google Drive, or just share it with you. Yeah, so here's my email. Please just email me and I'll send it to you if you need it. Okay. Reminder, office hours every Saturday, 12 to 2. If you have any questions about this or any other topics, I'll be happy to answer them. It's more one-on-one, so you get to ask more questions. As you saw with the MCAT questions I posted here, the MCAT-like questions I posted here, some of these are very simple, like this one, which most of you got right. And as long as you know what catalysts are, they're very like straightforward, very simple. Then there's other questions like this one, like this one especially, very tricky. So be careful. You just have to you have to recognize what is a simple question, what is, make sure to read everything carefully. Okay. Any other questions? I'll start. If you wanna email me a time that works for you, if you have any like specific questions, the link for the office hours, this Zoom link is for everything. Office hours, MCAT from now on. And I know there's been some problems with this this last week. From now on, this one Zoom link will be for office hours, for MCAT tutoring on Sundays. It will be for everything that Socratic Med does. Okay. As for office hours other days, maybe see if you can email me and we can maybe set something up like very quickly. If you do that, please come prepared to like with questions so I can answer them quickly. I don't have much time. I'm a full-time student as well. I don't have that much time. If you have a question right now, I still have some time because we ended a little bit early. Ask away. Otherwise, yeah, email me. Okay. Anything else? The second to last slide again. This one?
And no, not this one. The previous one. Not
This-
no. No. Not
This
this
one?
one. No. Yeah, this one. I mean,
Got it. Okay.
after that. Next
Oh,
slide.
this?
Yeah,
This?
this one.
Okay.
Yes.
Okay. So so you understand rate determining step, right? You understand this previous slide that I put like especially with my analogy with cooking, like there's a slow step. That's really what the whole thing is. In this one, the slow step is a second step. You know that, right? So the whole rate of the rate of the whole reaction would just be equal to the rate law for this one. Here, since we're already done, I'm just gonna alter it right now. Just to make it less confusing, it would be this. Sorry, 1 second. I'm just gonna alter some stuff. Okay. All right. So now it should be fixed. Okay. So you know that the rate law of this second step, it would be the rate law of the whole reaction of both steps, right? The rate law is this: rate equals the equilibrium constant, the rate constant of this step K2 times the concentration of both reactants, so N2O2 and O2, right? Like I mentioned, N2O2 is an intermediate. It's right here and right here. Intermediates, you can't include them in rate laws because you don't really know their concentration. Like you can't include like the concentration of an intermediate in a rate law. It means you have to find some way to like kind of get rid of this, like to kind of get rid of this and replace it with something else. We can use this property. So we know that equilibriums, the rate of the forward reaction, so the rate this way and the rate this way are equal. So, and we know what the rate laws for each way are. We know the rate law for this way, and we know the rate law for this way. So the rate law forward is K1, the equilibrium constant, times concentration of NO, times concentration of NO. So there's two reactants. So that's 2 NOs, NO2, NO squared. And we know that the rate of this reaction is K-1, the equilibrium the rate constant, times the concentration of this reactant, which is this, right? Well, and we set them equal to each other because we know that in an equilibrium, they're equal. So you notice how, I don't know if you remember from physics, 2 equations, 2 unknowns, you can solve it. The unknown we're trying to solve for is this rate and this concentration N2O2. We have 2 equations, we have 2 variables, unknown variables, meaning we can solve it. The way we solve for this is we just divide both sides by K-1. So we divide this side by K-1 and it cancels out. You just get N2O2, concentration of N2O2 on the right, and you get K1 times concentration of NO squared over K-1, right? And at that point, you know what you've isolated N2O2. You know what concentration of N2O2 equals. It equals this expression. It equals this thing. Well, now we go back to our original rate law. Like I mentioned, you can't have this in there, concentration of N2O2, because it's an intermediate. But you can replace it by doing this. Since you know these two things are equal, the left and right, you just replace what it is here with this expression. That gives you a whole rate of the whole reaction, which is what you're trying to solve in the end, K2, which comes from the original, then concentration of N2O2, which is this whole parentheses thing. So see, it's K1 concentration of NO2 over K-1. See, it's just this thing times the concentration of the other reactant for step 2, which is O2. As a note, O2 is not an intermediate because it doesn't get made in step 1. This is just something you add in. Oh, you can. How do you annotate? I should. Wow, I didn't know about this. This is very helpful. Okay. Do you want me to explain that again with annotations this time?
If that's possible, is it possible
Yeah.
for you?
Okay. Yeah, that is. I actually didn't know about this annotation. This would have been very, very helpful.
Yeah, I'm usually like
Okay.
comfortable with annotating. It would be easier to understand that way.
Okay. So, all right. So ultimately, you want to find this, right? Do you like do you understand this step? Like you're trying to find the rate of the whole reaction, right? You're trying to find this, right? And because this is the slow step, do you understand the slow step, fast step thing?
So not really.
Okay, so I'll go back a little bit. Okay. All right. Okay. What do I? Okay. So did you kind of understand what I meant with like the cookie? So a slow step, yeah. So it's kind of the same thing with the slow step. So if you were to have a reaction and the first step, which is in this case the slow step, the red one, if it took like 4 hours to happen, and then you had this second step, which is the fast one. After those 4 hours were done, and you had the second fast step, it would take 1 minute. How long did the reaction take? It took 4 hours, basically. It took like 4 hours. And so you really want to say that the rate of the whole reaction, both steps 1 and 2 combined, is really equal to the rates of this first slow step, right? Because the slow step is really what takes up 99.9% of the reaction time. And so you really can just equate them. It's not exactly equal, but there's such a big difference that the slow step will give you 99.9% of the reaction time, the reaction rate. Okay, does that make sense?
Yeah. That's...
So you can kind of think of it that the rate of this whole reaction, both steps, is just the rate of this one step because it's so much slower, right? And this, as you notice, is the exact same thing. So you have this fast step, equilibrium, in step 1. This happens like in seconds. And then this slow step, which takes a really, really, really long time to happen. Okay? So if the question asked you, what is the rate of this whole reaction from start to finish of both steps? You would be able to say that, here, annotate. You would be able to say that the rate of the whole equation, which is this, is just equal to the rate law of this step 2, right? The rate of this step 2 is equal to the rate constant, which is here, the concentration of the two concentration of the two reactants. So just NO2 and O2, right? Well, okay. So N2O2, you can see this thing right here, N2O2, it's an intermediate. So let me see if I can change the color. Yeah, okay. This is an intermediate. You see it appears here and it appears here. So it's an intermediate. You can't include intermediates in rate laws. It's just a rule. Like you're not allowed to do this, right? So you want to get rid of this. Like this is the rate law, and you know that this is the correct equation that will get you the correct answer that you want in the end. But you want to get rid of this like one term in this equation. You don't want to have this in the equation anymore because you can't use it. Well, how do we do that? Well, we have to figure out a way. So we know that this equilibrium has a certain property. So in an equilibrium reaction, the rate of the forward reaction is equal to the rate of the reverse reaction, right? Do you remember that? Okay, Janelle, you can go, yeah. Yeah, do you remember that? The rate of the forward reaction is equal to the rate of the reverse reaction?
Yeah.
Okay, so you know that the rate of the forward reaction is this, of going from here to here, is this, K1, the rate constant for the forward, times the concentration of the reactants. And since there's two of these, that's why it's squared, okay? And then you can set that equal to the rate of the reverse reaction. You know that the rate of the reverse reaction is just K-1, the rate constant for this reverse reaction going from N2O2 to NO, times the concentration of the reactant, which for this reaction is N2O2 here. Okay, right? Now, you notice that you have these two equations. So we have this equation, the rate equation, and you have this equation, right? They both have this term, which I'm going to highlight in red, or square in red, and concentration of N2O2, right? So just like you can in math or physics or anything else, you can combine these two equations into one equation, right? The way you do this is you have to isolate this concentration of N2O2 here. Get rid of these boxes to make it easier. All right, you have to isolate this term in this equation, okay? The way we do that is we just divide both sides by K-1. So I'm gonna, is it okay if I clear all the annotations I made so I can kind of?
Yeah, sure.
Yeah. So if you divide both sides by this term K-1, you can cross out, and then you're left with this. Concentration of N2O2 equals K1, concentration of NO2 squared all over K-1, because it's just divided, this whole thing divided by K-1, right? Well, now you know what concentration of N2O2 is equal to. You now know what this term is. So our initial goal was to solve this whole equation. And to do that, we wanted to get rid of this term, this N2O2. Well, now we can't get rid of it because we know what it's equal to, right? And now it's equal to just this whole thing. This is N2O2, what this is equal to essentially. Well, we've just proved that. So what we can do is we can just take this original equation, rate equals, we can rewrite it as this, because all we simply did was we took this N2O2 and we just replaced it with this, which we know is equivalent, which we know it's equal to, right? And so you can see that this, so I'm going to use different colors and clear again. Okay, so we have K2 here, K2 here. We have this N2O2, which is equivalent to this. And then we had this O2, which equals this. So you can see that this is just this, right? And now we've solved it. The question, yeah, if you're given a question like this on the MCAT, they'll give you what K1 is, they'll give you what K2 is, they'll K-1 is, they'll give you what K2 is, they'll probably give you what this is, concentration of NO, this thing, and they'll give you what this is, concentration of O2. And now you have everything you need to solve it. You have K1, K-1, K2. So this is good, this is good, this is good. They'll give you concentration of NO. This is good, and this is just squared. and they'll give you what O2 is. So this is good. And you have all of the variables you need to solve for the rate, which will be the answer.
So this is the equation that they have to know. Like, is there like a specific equation?
No, see,
no.
you have to derive the equation.
Uh-huh.
If you were to get this on an MCAT, I would expect at most you get one question like this. This takes a while. Like you mentioned, like I derived it. You would have to derive it just like I did. So you would have to write the rate law of step 2, which is here, I'll clear again. You have to derive the rate law of step 2. That would be step 1. That'd be the first thing you do is derive the rate law of this, the slow step, which I did here. Recognize N2O2 is the intermediate, can't be used. Next, you would have to find the rate laws of the K1 reaction and the K-1 reaction, and you have to set them equal to each other, which I did right here. Recognize N2O2 appears here, so you want to isolate it by just dividing both sides by this value, K-1, and putting it over here, which is what I did here. Now, you know N2O2 is equal to this whole thing. Now you can just rewrite it like this. Replace the N2O2 in this equation with this whole thing, which is what I did right here. And there you go. Now you can solve it. You just have to do those 4 steps, 5 steps. It does take a while, so I would really not expect them to have more than one question on it max. If they do, but it is important that you know it. Just in
I
case,
see.
right?
Okay, thank you. I truly appreciate it. Thank you.
No problem.
Thank you.
Anybody else have any other questions? I'd be happy to answer while I'm here. All right. Have a great day.